So good afternoon. When I saw the title of the talk, I was especially delighted, not just because I know Ramon always gives great talks, but also because back when I was an undergraduate, Vitaly Milman always emphasized to us, to his students, the power and importance of Alexandrov-Fenchel inequalities. So it's great to see more developments related to them. So please, Ramon.
Thank you very much, Yuval. Oh, yeah. Can everybody hear me in the back? Is it good? Yes? Yes? Okay. We assume so. So, yeah, thank you very much. It's a real pleasure to be here at this wonderful conference. There's so many wonderful talks. It's just there's many of them going on at the same time, actually. I wish, I could teleport myself to multiple different rooms. And to see old friends and it's really great. So I'm very happy to have been invited here. I'm going to tell you about the Alexandrov-Fenchel inequality, and let me tell you just a very little bit about some prehistory of this. Actually, the history of this inequality and its influence it had on mathematics is something that I can easily give an hour-long talk about, okay? So I will refrain from doing this. Let's start by, we're going to talk about convex bodies, okay? So I assume everybody knows what a convex set is, but let's just normalize, okay? So what is a convex set? It's a set such that if I pick any 2 points in the set, then the line between those points still lies inside the set, right? That's a convex set. And you have all seen this definition. And when you first see this definition, it's not much to look at, right? I mean, this is not, doesn't seem like a deep fact. But somehow or other, I mean, the notion of convexity is something that appears in almost any area of mathematics, right? I mean, probably almost all of you have used convexity in some non-trivial way in your work. And that is something that was obvious from the very beginning of the theory, okay? So the first person to really realize the importance of convexity was Hermann Minkowski. Minkowski was, he was a child prodigy. He was already doing mathematics in high school in the 1870s, 1880s, and he was working on number theory. Okay, he was not working on geometry or anything like that. And so he was working on old problems that date back to Lagrange and Hermite about whether there exist non-trivial integer values for which positive definite quadratic forms, right? So you have a positive definite quadratic form, and you want to know whether there exist integers, so just if you plug them in, you get a small value, right? And these kind of questions were studied by Hermite using arithmetic means, right? So using number theory, right? And Minkowski had a kind of brilliant insight, right? So what did he say? Well, let's look at all of the integer values. Let's do it in 2 variables, right? So the points where of 2 variables that are integers are just a lattice, right? And let's say the origin is over here. And let's say I have a positive definite quadratic form. Well, when is it small, right? When is, for example, a positive definite quadratic form less than 10? Well, that set is an ellipse, right? So we draw the ellipse here. Here's an ellipse. Okay. And now he said, well, let's forget about the fact that this is number theory. Here I just have a set, an ellipse, right? And he realized that if this ellipse has a large enough volume, it always must contain an integer point. And it's completely stripped the problem of number theory. That's a leap of faith if you think about it, right? And that was Minkowski's first observation. And then came the even bigger leap of faith, which is he started asking himself, what's so special about an ellipse? For a number theorist, the quadratic form is very natural because the quadratic form itself is determined by arithmetic operations. But Minkowski asked, what's so special about the ellipse? And he went back and looked at this proof. And what he realized is that in the proof of this theorem in number theory that he proved, the only thing he used about the ellipse was that it was convex, right? And symmetric, absolutely. So this is kind of the beginning of the story. And at this point, it was clear to Minkowski that the notion of a convex set is an important one. And he decided to study the volumes of convex sets, right? To develop a subject of the volume of convex sets. And he developed a theory, and he published this in a very influential paper in the year 1903. It appeared in the Mathematische Annalen. And this paper is a true masterpiece, and it introduces ideas and notions that they put the foundation of the field of convex geometry, but also it introduces, for example, the Minkowski problem, which played a huge role in the theory of geometric PDEs, nonlinear PDEs. It led to developments in algebraic geometry. It led to developments in all sorts of different areas that you would not expect. Okay, so let me not say much more about that. But for the purposes of this talk, let me also say that this paper of Minkowski introduced also some problems that remain open to this day. Okay, and so I'm going to talk about one of those problems. Okay, so that's what this talk is going to be about. So, so let me start by introducing just how the basic idea of how Minkowski thought about the volumes of convex bodies. Okay? So let me say up front, Minkowski's paper was in R3. Everything was in R3, but I'm going to work directly in Rn. Okay? So let's take a bunch of convex bodies. Convex bodies in Rn. Okay? So a convex body is a compact convex set. Nothing fancy. And one of the basic realizations of Minkowski is that the volume, if I think about the volume of a convex set, this is actually a polynomial. The volume is a polynomial as a function of convex sets. What does this mean? It seems a bit weird. So if we take the volume, let's plug in a linear combination of these sets, lambda 1 k1 plus lambda 2 k2 or lambda n km. Right, so what this means, this is simply the set of all points lambda 1 x1 plus lambda 2 x2 until lambda m xm, such that x1 is in k1, x2 is in k2, etc. That's called the Minkowski sum. Right? And now, of course, this is a function. Now this is an ordinary function of these coefficients lambda, right? And it turns out that when you take these lambdas to be non-negative, the volume is a homogeneous polynomial as a function of these lambdas. So you can write this as the sum I1 to In, right? So this is a homogeneous polynomial of degree n, which is the dimension of the space, of lambda I1 to lambda In, right? These are the monomials. And then there are some coefficients. And these coefficients, that they must depend on the bodies k1 to km that I plugged in. It's a very fundamental fact that the volume of convex bodies is a polynomial, and it has coefficients. And these coefficients are called mixed volumes. And it turns out these mixed volumes are always non-negative. Not only is it a polynomial, but it's a polynomial with non-negative coefficients. And these non-negative coefficients, they show up naturally like this, but they're not just some weird numbers. They have very natural geometric meaning. So there are many natural geometric quantities that are just very special cases of these mixed volumes. These are things you know, like the volume itself, surface area, mean width, and many more. I'm listing these three as examples because I'm going to get back to them later. But for example, you're an Rn, pick a random subspace of dimension k, project, compute the volume in Rk. Now average, for example, that's a very natural geometric quantity. That's also a mixed volume, etc. Okay, so there are many, many natural geometric quantities that are mixed volumes. And once you have this perspective, then you realize that in order to do geometry, what we would really like to do is prove inequalities between these mixed volumes. Right? And that's what Minkowski did. And so there is the kind of mother of all inequalities in this area, which one would think is called the Minkowski inequality. But of course, everything is called the Minkowski inequality, so we call it Alexandrov-Fenchel. Which is like the kind of uber inequality for mixed volumes. Right? Now, this inequality was actually proved by Minkowski in dimension 3. Okay? And it is due to Alexandrov in dimensions higher than 3. And it's not trivial. It does not a direct extension from dimension 3 to higher than 3. Let's not talk about Fenchel. Fenchel conjectured this inequality, but it's unclear whether he ever had a correct proof of it. You can ask me later. So what does this inequality say? Let me write it down. So we take a mixed volume. So a mixed volume is always an object that has n slots. This is a homogeneous polynomial of degree n, so a mixed volume has n slots, and it's a multilinear functional of each of these n bodies. But in the Alexandrov-Fenchel inequality, there are two bodies that play a special role, and the other ones, I'm just going to fix them on both sides of the inequality. And what this inequality is saying, that if I take the square of this coefficient, this is greater or equal than if I do the same thing, but I replace this by kk or ll. There. This is the inequality. So it kind of looks like a Cauchy-Schwarz inequality, right? I fix these bodies, C1 to Cn minus 2 are always the same on both sides. I'm going to call those reference bodies. They don't change. And what we change are these first two, right? So I go from KL to KK and LL, so it's almost like Cauchy-Schwarz, except the inequality goes kind of the wrong direction. This is a hyperbolic inequality. Now, of course, you would say, why do you just care about two bodies? But you can apply this, the mixed volumes are symmetric, right, under a change in the order of the bodies. So you can just apply this inequality over and over and over again to different sub-choices of these two bodies to get higher order versions of it, right? And this is standard stuff, so we don't focus. So it's a kind of log concavity property of the polynomials of this volume polynomial. And now the basic question that I'm going to talk about, and this question already dates back to Minkowski in 1903, and Alexandrov in his, this paper, this question appears in the original papers on this topic, which is, this is an inequality. When is there equality? When is there equality in this inequality? That's the question. Now, remarkably, at this level of generality, this question is open to this day. So let me try to explain. What this means. Why do you care about equality cases? What do they mean? What is the significance of that? So I'm going to give now a very classical example. It's a little misleading, this example, because it looks very special. But in fact, the higher dimensional case is much more, has much more diversity. But let's do this example. This is the example that appears in Minkowski's original paper in 1903. So we're now in dimension 3. And let's look at a very special case of this inequality, which is, what am I going to do? I have K, so K in R3 is a convex, any convex body. And B is the Euclidean ball. So whenever I write B, it's always the Euclidean ball. So I'm going to look at this inequality, VBKK squared greater or equal to VBBK, or let's say, VKKK, VBBK. Right, so this is just a special instance of that inequality. Right? So this K is always fixed. And then here I started with BK, and then I have KK and BB. So now the interpretation of this object is that this guy, this mixed volume over here, that's basically the surface area of K. So that's how you get, I'm cheating, there is a constant. The constant is actually 3, okay, or 1/3. I don't remember which one, but let me ignore these constants. So this is the surface area of K. This is the volume of K. And this so happens to be the mean width of K. So those are those two examples I wrote there. So here are 3 geometric parameters, and there's some kind of inequality between 3 geometric parameters. Right? And now what we're asking is, okay, we always have this inequality. What does it mean to have equality? Right? So when do we have equality in this inequality? So what does it mean, right? You always know that this is greater or equal than that. Right? So if, for example, I chose a body that was fixed, let's say I chose a body of volume 1. Right? So I've normalized it to a volume 1. So the volume is 1. And I fixed some mean width, 3. Right? I look at all bodies of volume 1 and mean width 3. Right? Then I know that the surface area squared up to whatever constant is always greater or equal than 3. Right? So now if I had equality, if I have such a body with equality, then I know that among all such bodies, the body that achieves equality minimizes the surface area. Right? Among all bodies where I fix the volume and the mean width. Now, if I didn't have the mean width, if I just had the volume, this is a very famous inequality called the isoperimetric inequality, right? If I fix the volume, and I want to minimize surface area, right? We've all blown soap bubbles when we were children, or when we're adults, as in my case. So if I fix the volume of air inside the bubble and I want to minimize the surface area, we all know the answer, right? This is the ball, right? But what would happen if I didn't just fix the volume, but I also fixed the mean width, right? So I took if I fixed the ball of volume 1, right? It's like this. But what if I forced it to be this wide on average? Right? Then the ball could no longer be the minimizer. Right? So the question is then, if I force the ball to be wider than it wants to be, right? What would be in that case, I have the volume 1, but I force it to be wider, right? Which body will now minimize surface area? So, you can ask people to guess, right? And I always get the same guess, which should be an ellipse or something like this. But this turns out not to be the answer. So the bodies turn out to be remarkably strange. Okay, so here is a ball. And now if I want to make it wider, what do? I take a point outside the ball, and I take its convex hull with the ball. So what I've done is I've added a little, it's like a party hat. You know those little hats that you get at parties, right? You stick a hat on the ball, right? And of course, now I've increased the volume, right? But I can rescale it back. I can rescale it back so it still has volume 1, right? But what I've done is I've increased the mean width, right? So if I fix a mean width larger than the mean width of a ball, then I can get something with the same volume of this form. And it turns out that this guy will be a minimizer of the surface area. But in fact, it's not the only one, because what can I do? We're going to a very, very, very good party, so we get 2 hats. Okay? I can do this, and again, I can play the game, so I can make these hats different sizes, right? But again, I can engineer it so that the volume is still 1 and the mean width is still 3, and that's also a minimizer. And in fact, I can put as many party hats on this as I want, right? So we can go to a fractal party, right, where I put a fractal pattern of these hats on the ball. There can be a countable number of them, for example, right? And that will still be a minimizer of the surface area under those 2 constraints. These are called cap bodies. That's the terminology of Minkowski, Cap and Körper. And all of them are minimizers. All of them are equality cases. And they solve this kind of strange isoperimetric problem. And you immediately see that this is a very unconventional kind of story, right? Because usually in isoperimetric theory, right, the minimizers are unique, they are smooth, they have positive curvature, or constant curvature, they have all these nice properties. And all these things are false here, right? The minimizers are not unique. There's like a huge family of them. And the minimizers have different combinatorial structures, right? So they're not combinatorially the same. They have these corners, so they're highly non-smooth. And they can have as many caps as you want, right? So this is a very unusual kind of thing from the point of view of variational analysis. Right? It turns out, so Minkowski in his paper noticed that these are equality cases. And then he writes, it can be shown that these are the only ones, along the line of equation 38 in my paper. Now you go to equation 38 and not clear, right? So Minkowski realized that they are equality in 1903, right? And it was finally proved by Bohl in 1943, so 40 years later. He has a paper that's called About the Conjecture of Minkowski, and that these are the only ones for this very special case of the Alexandrov-Fenchel. And for a long time, that was basically it. That was what was known about this book. The only constraint is that the caps cannot overlap. Okay? Because if you put, for example, a point here, then you would get this line to the other point, and that's not allowed, right? But as long as the caps are disjoint, there are no constraints. Or you have to, I'm only talking about convex bodies, right? So I'm only talking about convex. If you were not doing convex, then of course you could just, put points, just take a ball and just stick a line out of it, right? And you would increase the width of the body. So, are we good? So you see Minkowski already at that time interpreted this as a kind of very strange isoperimetric inequality, and he found these absolutely remarkable, which he writes in his paper. It's wrote in the first paragraph. I'm going to talk about extremely remarkable generalizations of the isoperimetric inequality. And he seemed to be fascinated by these things, but then he died of appendicitis only a few years later, and he never finished his business. Okay. So now the question is, so in general, for more general cases of the Alexandrov-Fenchel inequality, it remained open. And it turned out that in this very special case, there is a proof by Bohl, but it uses extremely special features of this example that are simply false for more general equality cases. So in fact, even the proofs that were known are completely useless to understand the more general situation. It has remained largely open, and it is a problem that appears in most textbooks on convex geometry. And what you see is that people for a long time believed that this problem was hopeless. Okay, and for example, there's a famous book of Burago and Zalgaler called Geometric Inequalities, and there's a section on this problem, and it's written the equality cases of Alexandrov-Fenchel inequality have not been characterized, probably because there are too many. It was believed there's so many of them, and there's no real reasonable characterization. Fortunately, not everybody believed this, and Rolf Schneider in 1985 published an extremely beautiful paper where he proposed conjectures. He proposed very detailed conjectures about what these equality cases might look like. And without this paper, nothing would have happened in this area, right? Because you don't even know where to look. Right? He proposed very detailed conjectures on what these equality cases should look like. It turns out that he missed an entire class of them. So we now know that there are actually many more than he conjectured. But nonetheless, he got the main ideas. So that led to some small progress in some special cases. For example, people studied them for zone widths, but in general, it's remained mostly. So before I tell you what we did, let me try to explain why this problem is difficult. So 3 or 6. Okay. So you know, usually when you prove an inequality, right? How do you prove equality cases of an inequality? Well, you have a proof of the inequality, right? And then, you know, once you prove the inequality, you go into the proof. And everywhere in the proof of the inequality where there was an inequality, right, you look what happens if it were equality. And now you stick all those things together, and then you end up with the equality cases of the inequality. Right? Unfortunately, the proof of the Alexandrov-Fenchel inequality doesn't go this way. So what happens in the proof of the Alexandrov-Fenchel inequality? So the proof of the Alexandrov-Fenchel inequality is modeled after an idea of David Hilbert. And the way it's done is you start by proving it under very good regularity conditions on the bodies. For example, you could assume that all of the convex bodies have smooth boundaries with positive curvature. Okay, so these are very, very nice bodies. Right? And in order to prove the inequality, that should be enough because these mixed volumes are continuous, right? You can approximate any convex body by a smooth body, right? So if you prove this inequality for smooth bodies, then at the end you just approximate and you get the inequality for general convex bodies. Right? So how does the proof work? Okay, here is how Hilbert's proof worked, which was adopted by Alexandrov. First, you assume that all of the bodies are smooth. That's the input. And then you have step one of the proof. Step one of the proof is to show that there are no non-trivial equality cases. Yeah, you prove the equality cases before you prove the inequality. Okay? So first you show that there are no non-trivial equality cases. Then you can bootstrap that to show that basically somewhere there can't be a sign change somewhere. So that you can only have one sign. So then you just start, right? So basically what do? You first assume they're all poles. Then you can just check this manually. Okay? This inequality. You just first take them all to be Euclidean poles. Then you show that you can never have equality when the bodies are smooth. And then you basically just show that because the sign of the inequality can never change, right? So if I kind of smoothly deform the balls into whatever other bodies with smooth bodies I have, then I still have the inequality. That's the way that Hilbert's proof. The trivial ones are where K is equal to L up to translation and scaling. So volumes are invariant under translation, and they are homogeneous, but this is a homogeneous inequality. So there are certain trivial equality cases where K is equal to L up to translation and scaling, and the point is that the fact that those are the only equality cases is the input to the proof. Right? But that's only true when the bodies are highly smooth. And you already see here in this picture that I drew, where is it? That you see these equality cases are not smooth. They have these corners, right? So it turns out that the interesting equality cases can only happen when the bodies are not smooth, right? But the entire principle behind the proof is that when the bodies are smooth, there are it's kind of a strange chicken and egg problem. So what happens is that in the standard proofs of this inequality, you'll never see interesting equality cases. They only arise in the limit once you take the limits to non-smooth bodies. That's when the equality cases arise. But if you go into the proof and you look at the objects that appear when you try to prove this for smooth bodies, you know this works with elliptic operators and nice things, And if you take now the limit in the proof where you go to non-smooth bodies, everything blows up. It becomes completely singular. Okay? So inequality situations everything in the proof is singular. And in fact, these singularities are what encode the equality cases. The reason these equality cases arise are precisely because of these singularities. Right? So the problem of understanding these equality cases really is the understanding of how these singularities arise in the Alexandrov-Fenchel inequality when you go to non-smooth bodies. And it turns out that this has there's really two very different kind of singularities that show up. They're analytic singularities. And they're combinatorial singularities. So these analytic singularities, they arise because, you know, convex bodies, their boundaries can be extremely non-smooth, right? For example, I gave you the example where you have a fractal pattern of these caps sticking out of the boundary. But these are really nasty objects. And if you want to work with such objects inside the proof, you'll have to work with geometric measure theory and very singular elliptic operators and things like this, right? So everything becomes extremely singular on the analytic side, okay? But even if you were to work with much nicer bodies, which are, for example, polytopes, right? Polytopes, which have a finite number of faces. These are purely combinatorial objects, right? Then the objects that show up in the proof are matrices, so they're not so bad. But then you see combinatorial singularities showing up. I can't really explain what these are without going into the details of the proof. But it turns out that because you have here n-2 convex bodies, and each of them have a very different structure, and it's the way that the structure of the boundaries of these bodies interact with each other that's causing the singularities to happen. And this is a kind of combinatorial characterization of these interactions is what shows up in the proof. Okay, so, and of course, if you really wanted to prove this equality characterization for general convex bodies, you would have both of these things happening at the same time. Okay? So with Yair, we made progress on both of these sides. Okay? And but we don't know how to put them together. So what we can do is we basically completely resolved this side of the problem. This side of the problem is understood completely, I would say. And we resolved this part of the problem in the setting where there are no combinatorial singularities. Okay? And we do not know how to combine these two things. Okay? So in this talk, I want to focus on the combinatorial side. Okay? And I'm going to write down something, right? And but we also have results here, and we require very different kinds of techniques to deal with these analytic singularities. So I'm just giving you some kind of hand-wavy ideas. All right, so now we've come to the part of the talk where I'm supposed to write down a theorem, I suppose, right? Unfortunately, well, you'll have to settle for never. The problem is that, as was predicted by Barago and Zagaler, there are a lot of equality cases. And to actually write down what they are, I would need a lot of definitions. Okay? So instead, I'm just going to write down some kind of, I'll write down a theorem with quotes. So, so I'm focusing now on the combinatorial side. Okay, so what I mean by the combinatorial side is that these reference bodies are polytopes, convex polytopes. When I say polytopes, I mean convex polytopes, but arbitrary polytopes. Okay? So then, the equality case, so equality squared equals k n minus 2 arises from three very different mechanisms. So there are three completely different reasons why these equality cases happen. The first one are the trivial equality cases that we already discussed, right? So there's translation and scaling. This inequality is invariant on the translation and scaling. So any equality cases have to be invariant on translation and scaling. Those are the easy ones, right? They appear even in smooth case. The second, and I would say the main mechanism for equality in most cases are the structure of the combinatorial structure of the relative positions of the normal cones of the boundaries of these reference bodies. So each of these bodies at every point on its boundary has a normal cone, a cone of normal direction. But if I take, if I take a normal direction, right, for each of these bodies, it might lie in a normal cone which points in a very different direction. They may have different dimensions. It's the combinatorics of how these normal cones interact with each other that is important. And this mechanism, too, was the extremely important insight of Rolf Schneider, that this mechanism plays an important role. That was the main insight of his conjectures. And in order to have a complete characterization, we had to add another mechanism that was not conjectured by Schneider, which is the relative positions of the affine hulls of these bodies. So unlike in, if I compute the volume of a convex body, if that convex body, if I'm in dimension n, but the convex body is n minus 1 dimension, right? I'm in dimension 3, but I look at a disk, flat disk. Its volume is 0, right? But mixed volumes are not necessarily 0 if you have lower dimensional bodies, right? If I take the mixed volume of a flat disk that goes like this and a flat disk that goes like that, it will be non-zero because the sum of those guys is a full dimensional convex body, right? So it could be that these reference bodies are all lower dimensional, or some of them are lower dimensional, and then the subspaces, right, the relative positions of the subspaces in which they live play a role in understanding the equality. And beside the fact that there are many of these, yes, there's a question? What am I supposed to do with it? Okay. So beside the fact that there are these three different reasons, one of the difficulties is that these three things happen in superposition with each other. So these don't happen separately. These are not distinct reasons. Actually, they can all appear at the same time, and they do all appear at the same time. So you have to kind of disentangle all of these phenomena when you're trying to prove them. Well, I mean, what you should really do is take any subset of these bodies and look at the dimension of the linear span of the subspace in which those bodies live, and you have to check this for every possible subset of these bodies. Right? So this depends the dimensions of those spans, but of every possible combination. Right? So and it's something similar over here, except you look at the dimension of the normal cone. Yes.
Which normal cone do you mean? Take
No. All normal cones. All normal cones. So you fix a direction, fix any direction u in the unit sphere, and then for each of the bodies, look at the normal cone of that body that contains that given direction u. So each of these normal cones, right, may have a different dimension, may be oriented a different way. And now you have to know something about the relative positions of those normal cones, of the normal cones of C1, all the, C1, C2 until Cn minus 2, that contain a fixed direction u. Now you have to do the same thing for all directions u. Okay, and that will determine the equality. Okay, so I'm not expecting you to understand what I wrote here. I'm just trying to give a a flavor of what kind of geometric characteristics of these bodies are showing up. But perhaps one of the main points is that these are really combinatorial in nature, right? I mean, we're talking about dimensions. I'm not talking about something quantitative, right? These are really combinatorial conditions. It's a statement about dimensions of the normal cones of these bodies, and that's it. Yes? Oh. Yeah, so the cap bodies will fit it. Cap bodies are, of course, not polytopes, okay? So they don't fit into that theorem. Cap bodies, however, we have a theorem here that cap bodies are a special case of also. So there is a similar story over there, and maybe I will write an example for polytopes and you will see. Okay, so did you have a, yes? Good. So let me try to just give an example to give you a flavor. So let me draw a kind of example that's kind of similar to these cap bodies. So we're in n equals 3. Now, n equals 3 is exactly the case where you don't have real combinatorial singularities, right? Because there's only one reference body. But it's easiest to think about. So, right? So we're looking at VKLC squared equals, right? VKKC VLLC. So let's take C to be just a cube. Right? Good, right? And then how are we going to take K and L? So initially, let me just think of K and L also being cubed. That's obviously an equality case. Right? If K and L are the same, obviously I have an equality case. Good, right? But now what I'm allowed to do is, for example, I'm allowed to take these cubes and I'm allowed to delete some of their corners. For example, here, let me delete this corner. I sliced it off like that, right? And here, let me delete this guy. Okay, so I've sliced off this corner. And let me slice some more corners. Here, let me slide that one. Okay, my drawing skills are, you can see, atrocious, but maybe it better go here, right? Okay. I hope you get my point despite the fact of the impossibility, three-dimensional impossibility of these pictures. Yes. No, numbers doesn't matter. Nothing matters here. So it doesn't matter what numbers you cut. It doesn't matter how far in you cut, okay? The only thing that matters is that you don't have one of these edges entirely disappear, right? So I could cut it like this also. Right? But I still have here a little bit of edge, or at least that the two triangles meet. That's also fine, okay? But I'm not allowed to go further in. Okay? So these are equality cases. So what happens here? So this mechanism 3 doesn't appear here because the reference body is full dimension. So we don't worry about 3. I'm not going to explain 3. I'm just going to explain 2. So what happens here is that the boundary of the body C here determines what are the good directions. It turns out in this case, the good directions are those that are not normal to a corner. Okay? So if I take any normal direction that is not normal to a corner, for example, I take a normal direction that's normal to this, right? Let's take a normal, here is a normal cone at this point of the body, right? That's not normal to a corner, right? So if I take a direction in here, like one that is normal to this edge, and now I look at these two bodies, and I look at the plane that touches the body with that normal direction, you see it's the same plane because I have the same little remnant here of an edge in both of these guys, right? And similarly, if I take a direction that's normal to a facet, like this, and I look at these two bodies, it's the same touching plane, right? Because these facets are still there, right? But if I take a direction that's normal to one of these corners, for example, I take a direction, this guy, right? The direction that's normal to that corner, and you see these two bodies are different, right? Because here I sliced off the corner, but here I didn't slice off the corner. But those directions that are normal to a corner, these are bad directions, and we don't care what happens in those directions. So the bodies are allowed to differ in the normal directions that are normal to a corner, but they're not allowed to differ in normal directions that are normal to an edge or to a face. Right? Now what happens this gives you a flavor, what happens in general is that I have n minus 2 reference bodies. And which vectors are good directions and which directions are bad directions? Right? So I fix a direction u, I want to determine whether it's good or bad. It depends on the relative position of the normal cones of each of these bodies that contain that direction u. So from the combinatorics of the boundaries of these bodies, I can make a rule that tells me which directions are good and which directions are bad. And then what has to happen is that in order to get equality, K and L have to be the same. They have to have the same supporting hyperplanes in all of the good directions. But they are allowed to differ in the bad direction. And this is just one very, very simple example of this phenomenon. Again, I'm giving a flavor. You know, we could write it down formally with definitions, but I hope you get some kind of idea of what is going on. K is a cube. No, because if L is a ball, right, then there will always be a normal direction to right? I mean, if L is a ball, then it will necessarily be the case that there will be some direction that's normal to an edge where the ball is shorter than the cube, right? So you cannot have equality in that case, right? But you see in this case, right? You see in this case, K and C are both cap bodies and L is a ball. You see what happens in this case, right? So I have two of them are cap bodies and one of them is just the ball, right? And you see the ball and the cap body are the same in all normal directions that are not normal to one of the corners, right? And that's exactly the same phenomenon that you see over here. Good. In my last 5 minutes, do I have 5 minutes? I want to talk about something completely different. So let's switch gears and talk about combinatorics. So in combinatorics, we're now not talking about collapse, I'm just talking about pure combinatorics. People who work in combinatorics, they like to count things. Okay, that's kind of their job. And in many combinatorial problems, people have sequences of numbers that arise as certain enumerative quantities. So, if I have a sequence non-negative integers, it's called law concave. If ni squared is greater or equal than ni plus 1, ni minus 1 for all I. This is a law concave sequence of non-negative integers. And it was noticed very long ago that it turns out that in combinatorics, often you get sequences of counts of something, and they very often form law concave sequences. And it's kind of a mystery why this is true. It was more of a mystery than it is now, but kind of a mystery why it's true. And in many cases, these were conjectures. And in recent years, there has been huge breakthroughs in resolving many of these conjectures. I maybe say a little bit about it. But let me give an example. So this is one of the earliest examples due to Stanley. It said, so let's take P. This is an arbitrary partially ordered set. Let me write it like this. So let's need P is a set with a point x, y1 to yn minus 1. So it's a set of size n, any partially ordered set. So, right? So I take any partial order on this set. And if I have a partial order, I can always add more relations to make it a linear order, right? To make it a complete order. And the question is, in how many ways can you do this? Okay. So Stanley was interested in the following quantity, which arises from conjectures in the 70s, which is the number of linear extensions. So this is just the number of ways in which I can extend the partial order to a total order, right? It's not unique, right? There may be many different ways. Such that in this total order, the element x has rank I. Okay. And now the question is, if I have a distinguished element x, right? I want it to be, let's say, first in the order, last in the order, in the middle of the order, right? Which one will be bigger? Which one can I do in more possible ways, right? So it was conjectures in the 1970s by Rivest and by, I've forgotten, Fenchel, I think, but I have to look it up, that these sequences are law concave. And nobody knew how to prove this until Stanley realized that this is just a special case of the Alexandrov-Fenchel inequality. What did he do? So Stanley's idea is he just cooked up some polytopes. So you give me any partially ordered set like this, with a distinguished vertex x. And what Stanley did is, given P, he cooked up some polytopes, K and L. These are variants of order polytopes, if you know what these are, such that I can just represent these numbers as n minus 1 factorial times the mixed volume of K some number of times and L some other number of times. Maybe I minus 1 and n minus I, or something like this, maybe the other way around. Okay? And once you have this representation, the formula, once you have this representation, then of course law concavity is immediate from the Alexandrov-Fenchel inequality. Because if I replace KL by KK and LL, that's exactly taking I to I plus 1 or I minus 1. Right? That proves law concavity. And this was very influential. And for example, in recent years, there was been big breakthroughs of Jun Han and other people who proved long-standing conjectures about other combinatorial sequences that are law concave. The problem was that these other sequences cannot be represented as mixed volumes. And in essence, what they realized is that they don't need to represent them as mixed volumes. You could just reprove the Alexandrov-Fenchel inequality directly for these objects. The proofs of these inequalities are actually basically the proof of the Alexandrov-Fenchel inequality. And once you reprove the Alexandrov-Fenchel inequality, you get the same kind of phenomenon. Okay. So what can we do now? Well, we can ask what happens when this inequality becomes equality, and what does it mean? What does it mean that the law concave sequence has equality? That means you have a geometric progression in the sequence. And therefore, if you were to understand the equality case of Alexandrov-Fenchel, for example, here, you can ask, can I identify for a given partial ordered set where the geometric progressions appear in the sequence? What kind of progressions you can get? What happens? And I don't have enough time to draw for you a full picture, but it turns out that we can, in fact, do these things. So for example, for this inequality of Stanley, we have a complete characterization. You give me any partially ordered set, I can explain to you exactly what geometric progressions appear, where in the sequence they appear, how long they are. I mean, we can compute these things, which is quite surprising because these numbers Ni, these are very hard to compute. In fact, the complexity theory tells us these are very hard to compute. But we understand exactly where the geometric progressions appear. And one of the fascinating things, let me end with saying this, is that we now know that Alexandrov-Fenchel type inequalities show up in many places. And even if they're not the ones from convex geometry, similar inequalities show up in many places. They show up in combinatorics. They show up in algebraic geometry. They're called Chovansky-Tessier inequalities. And I believe that the kind of mechanisms that are coming out of this theorem are quite universal. They should be universal, and they should extend to all of these other situations in some form or another. And at the moment, this is largely conjecture, but there has been progress on this, particularly in algebraic geometry. And I think it's interesting to see the same phenomena appearing in different areas of mathematics. So let me end there, and thank you very much for your attention.
Questions? Yes.
Okay. Can you show some crucial ideas to translate the equality case, these three mechanisms to the combinatorical applications and algebraic geometry framework? Thank you.
Which combinatorial applications? Do you mean this one, or do you mean to, for example, these other ones that cannot be described in terms of mixed volumes? So this one, you see, in this application, it is the Alexandrov-Fenchel inequality, right? The Alexandrov-Fenchel inequality, so our theorem applies, right? So given any partially ordered set, there's a completely explicit construction of this K and L. If you write it down, that's a manual construction, right? So there's explicit construction. So if you just plug these two polytopes here into this theorem, right, it'll explain to you exactly when you have equality. The problem is that it explains when you have equality in terms of the geometry of these two polytopes K and L. And the main difficulty now is to take this geometric information about K and L and translate it back to combinatorial information about the partially ordered set, which is completely explicit. Our conditions are not geometric, they're combinatorial. And that requires work, okay? So you don't get that for free. That part, translating from the geometry to the combinatorics, required additional work. And basically what happens is that when you write down what these conditions mean, okay, for these particular polytopes, you get basically a system of linear equations. And you have to show that what it means for the system of linear equations to have solutions or not have solutions. Right? So there is work involved in interpreting this geometric information combinatorially.
And this is in your paper?
For this inequality, it's in our paper with the Alexandrov-Fenchel. We have extended this separately, Yair and myself, into different papers to various other inequalities of this kind, where we see different phenomena. And in fact, one of the most surprising things to me about this story is that you see, it's not so surprising for polytopes. If I can cook up arbitrary polytopes with arbitrary geometries, right, that you can have many different equality cases, right? Because you have a lot of freedom. You have here n polytopes that you can cook up. But it turns out that all of these three mechanisms appear in these kind of combinatorial inequalities. So these mechanisms are not that esoteric, they appear naturally in a combinatorial application that had nothing to do with Alexandrov-Fenchel. But that translation from geometry to combinatorics requires work, and we know how to do that, but it actually requires a case-specific work. We don't have a general technique to do this translation.
So classically, besides the original proof, I guess there was also Chovansky's proof of Alexandrov-Fenchel, which I don't know if you view as completely different, but do these insights give you a new proof that doesn't require smoothing of the original inequality?
No, we have a new proof, but it requires smoothing. I believe that these proofs are very fundamental. Okay, so the smoothing, it has to be. Because we can see in the proof that if you have non-trivial equality cases, that's exactly when everything breaks down. It seems that then you have no freedom to prove the inequality, right? So it seems that if you wanted to do that, you would first have to understand the equality cases before you prove the inequality, and that seems completely hopeless. There are various different variants of the classical proofs. They work slightly differently, and I prefer some to others, but there are various different variants. And then there is Chovansky, which is completely different. But what Chovansky does is very nasty because, You know, there's an equivalence between convex geometry and toric geometry, right? But toric varieties are very special kind of varieties. And then what Chovansky does is he says, okay, we take this toric variety, which has a complete translation to convex geometry. And then I take a generic hyperplane section of this thing. But this section is not toric, right? So Chovansky's proof exits convex geometry. Maybe, yes, presumably, but we have no interpretation of this. You know, it has an interpretation as algebraic geometry, but it has no interpretation in terms of convex geometry. His proof kind of exits convex geometry, which means that we don't really understand, right, what is going on. But I assume, because it's generic, that there's some kind of smoothing, but I don't understand this well enough that to be able to talk about it intelligently.
So one more case where somehow this difference between the smooth and non-smooth case was very prominent is Borsuk's conjecture, where you know, it was true and easy and almost immediate for smooth bodies and then false in general.
I have nothing to say to you, Yuval, about this. No, I'm sorry. I don't know any connection between those two things. It would be very interesting, but yes.
Because there also we see a lot of richness of structure once we exit the smooth category. Yes. While in the smooth, they're just, well, the conjecture is true trivially because it's true for the ball.
And that's what, one of the things that makes these questions fascinating.
Any other questions?
How to characterize their relative positions?
Oh, this is something we can do. I mean, you know, if you give me a polytope, I can compute the dimensions of the faces, and you know.
Maybe you think it's the surface area method?
Yeah, they're just. It's completely explicit in terms of dimensions of the Minkowski sums of the faces. So this is something we can compute by hand. I mean, you know, it's not hard to compute these things.
Is this on? Oh, okay.
Doesn't matter.
Yeah. So in the equality cases that you generate when all the CIs are polytopes, are the equality cases also polytopes?
You mean KNL?
KNL, yeah.
Okay, KNL do not have to be polytopes, but that turns out not to be a big deal because it turns out that when, and that's one of the first things we do in the proof, when C1 to Cn minus 2 are polytopes, then, and K and L are arbitrary, but you have equality, we can always replace K and L by polytopes without changing any of these three mixed volumes. So it turns out not, this particular aspect turns out not to be important in the proof. That's something that comes out of the...
But there are cases of equality when the KL are not polytopes.
Oh, absolutely,
all the other
absolutely. So the theorem doesn't require that K and L are polytopes, but this doesn't create any complications in the proof. The smoothness that is used in the proofs are of C1 to Cn minus 2, not of K and L. So, yeah.
Okay, one more question.
Yeah. Yes.
If the proof in the smooth case depends on elliptic theory of some elliptic differential equation,
yes.
Maybe the proof in this, in the case of polytopes, for instance, would correspond to some sort of differential operator on graphs or simplicial complexes or something like that, right?
Well, in the case of polytopes, it's just a matrix. The analog of this elliptic operator is just a matrix. That's not a big deal. The difficulty is when you have general convex bodies, and this is the other branch that I didn't talk about, the analytic singularity. We have a way of constructing singular elliptic operators abstractly that capture this situation. We know how to construct them. We construct them abstractly just using Friedrich's extension of some, something. So we know how to do this, but we can't manipulate them. But I would have to explain to you in more detail what the issue. There is a very specific obstruction there to making progress, and that we don't know how to handle. But yes, one needs to pass to some kind of singular elliptic operator. But in the polytope case, they're just matrices, so that makes everything very nice.
Let's thank Ramon for a wonderful.
Thank you very much. Thank you.